Hello everyone, I am Biresh Roy. I am currently pursuing my fourth year PhD in the Department of Physics, Indian Institute of Science, Bangalore. I am currently working in the field of experimental condensed matter physics. In this video, I will be discussing all the questions from the topic solid state physics came in the exam GATE Physics 2020. This question is from the GATE Physics paper 2020. This is a NAT, that is numerical answer type question having 1 mark. The topic of the question is solid state physics. Specifically, this question was asked from the chapter crystal structure. So in the question, a two-dimensional lattice structure is given. The question is the number of distinct ways the primitive unit cell can be constructed for this two-dimensional lattice as shown in the figure is. So we have to find how many ways we can construct the primitive unit cell with this two-dimensional lattice structure. We know primitive unit cell is the smallest volume cell possible in the lattice structure. So primitive unit cell is the building block of that lattice structure. All the lattice points belonging to a primitive cell lie at its corner. Therefore, the effective number of the lattice points in a primitive unit cell is 1. Let us see the number of distinct ways of the constructing the primitive unit cell for two-dimensional lattice structure. So, according to the definition of primitive unit cell, the lattice points lies at the corner of the primitive unit cell. So now we'll see how can we connect the 4 lattice points in this two-dimensional lattice structure in different manners to form the primitive unit cell. Possibility 1 is by connecting these 4 points we can get a primitive unit cell for this two-dimensional lattice structure. So this is number 1 possibility. Number 2 possibility is this. So connecting these 4 points we can get another primitive unit cell for this two-dimensional crystal structure. Third possibility is this. So connecting these 4 points we will get the third possible primitive unit cell. Fourth possibility is again an parallelogram connecting by these 4 points. And the last and fifth possibility is connecting these 4 points to get the parallelogram shaped primitive unit cell for this two-dimensional crystal structure. So there are total 5 possibilities. So number of primitive unit cell in two dimension is 5. From this solution we found that for this two-dimensional lattice structure the number of distinct ways the primitive unit cell can be constructed is 5. This question was asked in the GATE Physics paper 2020. This is a MCQ type question having 2 marks. The question is from the topic solid state physics. The question is, consider a one-dimensional non-magnetic crystal with 1 atom per unit cell. Assume that the valence electrons, number 1, do not interact with each other, and number 2, interact weakly with the ions. If n is the number of the valence electrons per unit cell, then at 0 Kelvin, option A, the crystal is metallic for any value of n. Option B, the crystal is non-metallic for any value of n. Option C, the crystal is metallic for even values of n. And the last option, option D, the crystal is metallic for odd values of n. So let us see which option is correct. So here we are given one-dimensional non-magnetic crystal has 1 atom per unit cell. Let the atom have n valence electrons. Now there are 2 assumptions we have to consider according to the question. Those are, there is no interaction between electrons, so no electron-electron interaction. And the second assumption is electrons have weak interaction with the positive ions, that is electron-ion interaction. So these are the assumptions basically we consider in the root theory of metal. Now we can have either even values of n, that is number of valence electrons per atom, or odd values of n. So for even values of n, if we choose n equals to even value at T is equal to 0 Kelvin, these electrons will make either a covalent bond or van der Waals bond. Example, silicon, germanium, carbon, this type of atom has 4 or even electrons in their valence shell, and they make covalent bond with their 4 nearest neighbors. Now the second case, odd values of n. If we choose odd values of n, then at T is equal to 0 Kelvin, the electrons will make either ionic bond or metallic bond. Since here we have only one atom in the unit cell, that is monoatomic basis, while bonds require two electronegative and electropositive atoms in the crystal. So ionic bonds are not possible in our case. In this case, most favorable bond is metallic bond. In the metallic bond, the outer energy levels of metals atoms, the s and p orbitals, overlaps. The electron participating in the metallic bond is not shared with a neighboring atom, nor it is lost to form an ion. Instead, the electrons form what may be termed as electron sea, in which valence electrons are free to move from one atom to another. Let us consider some example. Sodium, which has valence electrons n equals to 1, aluminium, which has valence electron n equals to 3, silver, which has valence electron n equals to 1, gold has valence electron n equals to 5. So all these elements are basically metals having odd number of electrons in their valence shells. So sodium, aluminium, silver, gold, etc. are few metals in which total number of valence electrons are odd. So the one-dimensional crystal will be metallic for odd values of n, that is odd number of valence electrons in the valence shell. So our option D is correct. So we have solved this question and we found that the last option, option D, the crystal is metallic for odd values of n. That is the correct option. This question is from the GATE Physics paper 2020. This is a MCQ type question having 2 marks, and the topic of the question is solid state physics. Specifically, this question was asked from the chapter lattice vibration. The question is, consider a two-dimensional crystal with 3 atoms in the basis. The number of allowed optical branches, that is n, and the acoustic branches, the number of acoustic branches is m, due to the lattice vibrations are. So there are 4 options given. The value of n equals to 2 and m equals to 4. Option B, value of n equals to 3 and value of m equals to 3. Option C, value of n equals to 4 and value of m equals to 2. And the last option, option D, the value of n equals to 1 and the value of m equals to 5. So let us see how to solve this problem. Now let us discuss the number of phonon branches in a solid. Let the number of atoms in the primitive cell of the solid is P. So basically the number of bases in the primitive cell is P. Now let us follow this chart. For one dimension, the total number of phonon branch will be P, where P is the number of bases. Now in one dimension only one acoustic branch is possible, so the remaining phonon will be in optical branch. So number of optical branch phonon will be P minus 1. Now for two dimension, total number of phonon branch will be 2 times P, where P is the number of bases. So basically we have to multiply the dimensionality of the system with the number of bases. So total branch will be 2p in 2 dimension. In 2 dimension only 2 acoustic branch is possible in either x or y direction. So the remaining number of phonons in the optical branch will be 2p minus 2. In 3 dimension, the total number of phonon branch will be 3 times p. So, acoustic branch phonon will be 3. So, basically the acoustic branch number of acoustic branch phonon is depends on the dimensionality of the system. So, it will be 3 here. So, number of optical branch phonon that will be remaining phonon branch, that will be 3p minus 3. Now, it is given that the given crystal is 2 dimensional with the number of bases is 3, that is p equals to 3, and the dimensionality of the system is 2. So, total number of phonon branch will be 2 times 3, that will be 6. As it is 2 dimensional system, so number of acoustic branch will be m equals to 2. So, remaining phonon branch will be in the optical branch, so that will be number of optical branch n equals to 6 minus 2 equals to 4. So, this set n comma m is basically 4 comma 2 in our case. So, option C is correct. So, the number of allowed optical branches and the acoustic branches for this 2-dimensional system, crystal system with 3 atoms in the basis is 4 comma 2. So, option C is correct for this question. This question was asked in the GATE Physics paper 2020. This is a numerical answer type question having 2 marks, and the topic of the question is solid state physics. The question is, consider a simple cubic monatomic previous lattice which has a basis with vectors r1 vector equals to 0 and the second basis r2 vector is a by 4 times x cap plus y cap plus z cap, where a is the lattice parameter. The Bragg reflection is observed due to the change in the wave vector between the incident and the scattered beam as given by capital K vector equals to n1 times g1 vector plus n2 times g2 vector plus n3 times g3 vector, where n1, n2, n3 are the integers and g1, g2 and g3 vectors are primitive reciprocal lattice vectors. For n1 equals to 3, n2 equals to 3 and n3 equals to 2, the geometrical structure factor is, so we have to find the geometrical structure factor for this kind of lattice with this given n1, n2 and n3 values. Let us see how to solve this problem. For a simple cubic monoatomic Bravais lattice which has a basis with vectors r1 vector equals to 0 and r2 vector equals to a by 4 times x cap plus y cap plus z cap, where a is the lattice parameter. So, the basis atoms are lying at the points 0, 0, 0 and a 1 by 4, 1 by 4, 1 by 4. According to the quotient, the capital K vector is basically change in the wave vectors of the incident and scattered X-ray beam, and that is also given by n1 times g1 vector plus n2 times g2 vector plus n3 times g3 vector. Here n1, n2, n3 are the integers. Those are analogous to the Miller indices, that is HKL, and g1 vector, g2 vector and g3 vector are the primitive translational vectors in reciprocal space. So, those are reciprocal lattice vectors, and that is usually denoted by A star vector, B star vector and C star vector. Now, the geometrical structure factor S as a function of n1, n2 and n3 is expressed by S as a function of n1, n2 and n3 is equals to sum over j exponential of 2 pi iota times xj times n1 plus yj times n2 plus zj times n3. Here the sum is over the basis and xj, yj, zj is the coordinates of the jth basis. Now we have two bases in our system. The basis atoms are available at 0, 0, 0 and 1 by 4, 1 by 4, 1 by 4. Hence, j will be having values 1 and 2 only, and for the j values x1, y1 and z1 will have the value 0, 0, 0 and x2, y2, z2 will be 1 by 4, 1 by 4, 1 by 4. So, we will use these values in the expression of the structure factor. So, we will get S as a function of n1, n2 and n3 will be sum of j, and j value will take 1 and 2, exponential of 2 pi iota xj n1 plus yj n2 plus zj n3. So, we will have exponential of 2 pi iota 0 into n1 plus 0 into n2 plus 0 into n3, because for the first basis the coordinate is 0 comma 0 comma 0, and for the second basis we will have exponential of 2 pi iota times 1 by 4 times n1 plus 1 by 4 times n2 plus 1 by 4 times n3. So, we are having that the structure factor S is equals to exponential of 2 pi iota times 0 plus exponential of 2 pi iota by 4 times n1 plus n2 plus n3. So, this term will give exponential of 0, that is 1, and the second term will give exponential of pi iota by 2 times n1 plus n2 plus n3. Now, according to the question, n1 equals to 3, n2 equals to 3 and n3 equals to 2. So, the geometrical structure factor is S as a function of 3 comma 3 comma 2 equals to 1 plus exponential of pi iota by 2 times 3 plus 3 plus 2. So, this will give exponential of 4 pi iota. So, we will have the structure factor 1 plus exponential of 4 pi iota. Now, exponential of 4 pi iota is basically 1. So, we will have the structure factor 1 plus 1, that is 2. So, the geometrical structure factor for n1 equals to 3, n2 equals to 3 and n3 equals to 2 is 2. So, we solved this problem and we found that the structure factor for the simple cubic monatomic Bravais lattice with 2 bases is 2 for this given n1, n2 and n3 values.